In this work, we propose a novel paradigm named Code as Monitor, which leverages vision-language models for both reactive and proactive failure detection via constraint-aware visual programming. As expectations grow for robots to handle long-horizon tasks within intricate environments, failures are unavoidable. Therefore, automatically detecting and preventing those failures plays a vital role in ensuring the tasks can eventually be solved, especially for closed-loop robotic systems. There are two modes of failure detection: reactive and proactive. As depicted in the figure, reactive failure detection aims to identify failures after they occur. For example, recognizing that lobster lands on the table indicates a delivery failure. In contrast, proactive failure detection aims to prevent foreseeable failures. For example, recognizing that a tilted pan could cause the lobster to fall out can lead to a delivery failure. Both detection modes are even more challenging in open-set scenarios, where failures are not predefined. With the help of large language models and vision language models, recent studies can achieve open-set reactive failure detection as a special case of visual question answering tasks. However, these methods often bear compromised execution speeds and coarse-grained detection accuracy due to the high computational costs and inadequate 3D spatiotemporal perception capability of recent large language models or vision language models. Moreover, open-set proactive failure detection, which has been less explored in the literature, presents even severer challenges as it is required to foresee potential causes of failure and monitor them in real time with high precision to anticipate and prevent imminent failure. Simply adapting LLMs/VLMs cannot meet such expectations. In this work, we aim to develop an open-set failure detection framework that achieves reactive and proactive detection simultaneously, not only benefiting from the generalization power of VLMs, but also enjoying high precision in monitoring failure characteristics with real-time efficiency. We successfully address this by formulating both tasks as a unified set of spatiotemporal constraint satisfaction problems, which can be precisely translated by VLMs into executable programs. Such visual programs can efficiently verify whether entities, for example, robots, objects, or their parts in the captured environment maintain or achieve required states during or after execution, that is, satisfying constraints, so as to immediately prevent or detect failures. We name this constraint-aware visual programming framework as Code as Monitor. To enhance the accuracy and efficiency of constraint satisfaction monitoring, we propose constraint elements by means of abstracting the constraint-related entity or part segments from the observed images into compact geometric elements, for example, points, lines, and surfaces. It simplifies the monitoring of constraint satisfaction by tracking and evaluating the spatio-temporal combinational dynamics of these elements, eliminating the most irrelevant geometric and visual details of the raw entity's parts. Here we show the pipeline of Code as Monitor. Given task instructions and prior information, the constraint generator derives the next subgoal and corresponding textual constraints based on multi-view observations. The painter maps these constraints onto images as constraint elements. The monitor generates monitor code from these images and tracks them for real-time monitoring. If any constraint is violated, it outputs the reason for failure and triggers replanning. This framework unifies reactive and proactive failure detection via constraints, more generally abstracts relevant entities or parts through constraint elements, and ensures precise and real-time monitoring via code evaluation. Given a constraint, our model ConSeg, which is a multi-granularity constraint-aware segmentation model, generates instance-level and part-level masks across multiple views, which are projected into three-dimensional space. Through a series of heuristics like voxelization, clustering, and connecting, the desired elements are produced. Once all elements are obtained, they are annotated onto the original multi-view images. Here we display the annotation result of one element. Since the textual constraint does not explicitly specify relevant entities, parts, we present our ConSeg, which can perform precise constraint-aware instance and part-level segmentation and is capable of logical reasoning and certain open-set adaptation. Here we display the part-level segmentation, which will output the desired element type and mask. We evaluate code as monitor across simulators and a real-world setting. In the Clipboard simulator, our code with proposed elements successfully enhances monitoring of 3D spatial relationships of entities in the environment, facilitating both reactive and proactive failure detection and leading to more accurate counting. In the Omni Gibson simulator, we also find that code with proposed elements can detect richer failures with lower computational cost compared to frequent querying VLMs. This improvement stems from proactive failure detection, which prevents more severe failures ahead in real time for timely replanning while generating code only once per sub-goal. We also evaluate the code as monitor framework on long horizon tasks within cluttered scenes, focusing on tasks with instructions and items not present in the training data to test its generalization capacity across different scenarios. We discover that elements abstract constraints and relevant entities effectively. More importantly, the combination of reactive and proactive failure detection with an open-loop policy creates a closed-loop system. Enabled by the potential diversity of the structured associations of constraint elements, this minimalist scheme is generalizable to open-set failure detection for unseen entities and scenes. Therefore, we demonstrate more visualization of constraint-aware segmentation results of both instance-level and part-level, from out-of-distribution data, like RoboFail dataset, Open 6-door benchmark dataset, and RT1 dataset. More detailed experiments and ablation studies can be found in the main paper, and more demo videos can be found on the project website. Welcome to contact with me if you have any questions. Thanks for your attention.